Lesson I and 2, we're talking about understanding irrational numbers. We talked about rational numbers in the last lesson, so today we're looking at irrational numbers. Most of the sets of numbers listed on the page here we have talked about, page IN8. One set we did not talk about is the natural numbers. Natural numbers they sometimes call counting numbers. Just starts with 1, 2, 3, and so on. So very similar to whole numbers we talked about the other day, just there's no donut hole, no zero included in the natural numbers. So example 1, there's a Venn diagram showing the relationship between these. Rational numbers includes all these other sets of numbers. It includes integers, it includes whole numbers, it includes natural numbers. And as you'll notice as we go along, we're getting into smaller and smaller groups. Okay, integers, less numbers that are integers than rational numbers. Whole numbers, less things that are whole numbers than integers. And then natural numbers, only difference is the zero, but less than there are whole numbers. So the question on example 1 is how would we classify this number? 0.247583326 ... Anybody see a pattern on that? No. Okay. Keeps going, doesn't repeat. We kind of mentioned it the other day. That would be irrational. Okay. So the book first just says it is not a rational number, and so that means actually that it's an irrational number. So irrational number, I think we already got this the other day. Irrational number is the decimal keeps going and doesn't repeat. You got that down? Decimal keeps going, doesn't repeat. Okay. So some examples you can see here of irrational numbers. Square root of 2. If you try to take square root of 2, a number times itself to equal 2 doesn't come out evenly. The next decimal there's a nice pattern to it, but it's not the exact same thing repeating every time, so that would be irrational as well. Pi we've talked about before. It's about 3.14, but the decimals keep going. Negative square root of 3, similar to the square root of 2 we talked about earlier. Decimals keep going, don't repeat, so that would be irrational as well. Okay? So that's the main thing. Decimals keep going, don't repeat, it's irrational. Okay? So we'll look at the try it. Try it asks us to classify these numbers as rational or irrational. So just look and see which group you would categorize those as. So one of these, pi, would be irrational. We already talked about it's about 3.14. Decimals keep going, don't repeat. Negative 17 would be rational, because we could write that as negative 17 over 1, or you could just say, well, decimals don't keep going and not repeating themselves. No decimals even there, so that's got to be rational. The 0.76 repeating would be rational. Remember we talked about the other day, repeating is rational. We'll talk more later, but that you could write as 76 over 99 as a fraction. 3 and 275 thousandths is rational. We could write that as a fraction with two integers if we wanted to, or you could say the decimals end or terminate. And as you might guess by the table how they have it set up here, the last two are going to be irrational. You might say, well, that's the only spot for them. Well, we can't always judge it by that, but that is the case here. Decimals keep going, don't repeat themselves. Look at example 2. They want us to identify square roots as irrational numbers. So square root, what we're doing is looking at a number multiplied by itself equals the original number. So for example, we could talk about here the square root of 1 is equal to 1, because a number times itself that equals 1. Well, 1 times 1 equals 1. Square root of 4 is 2, because 2 times 2 equals 4. Square root of 9 is equal to 3, because 3 times 3 equals 9. And those numbers, like we talked about, those are some examples, 1, 4, and 9. Those are called perfect squares. So perfect squares, like the book talks about, it's a number that is the square of an integer. So 1 squared equals 1. 2 squared equals 4. 3 squared, 3 times 3 is 9. 4 squared, 4 times 4 is 16. Okay? And it's called a perfect square. One way of looking at it here, if you'll notice the green squares on the page in your book, notice they actually make squares. Okay? Overall, it makes a square, and then we can look at how many smaller squares they have inside of them. Okay, so a 3 by 3, 3 times 3 is 9. If we went a step further, 4 by 4, 4 times 4 is 16. We'd have 16 squares in it. So what's going to happen with these, with the square roots, is that if it's not a perfect square, then it's irrational. We could actually do this if you wanted to check on your calculator, just to get an idea. So like we could take the square root of 3. Okay, the book's saying square root of 3, which they're saying it's irrational. If you take square root of 3, what you can do to do square root of 3 is if you do the second button, which is yellow or blue or something in the top left corner, hit the second button, and then if you hit the x squared button, right above the x squared button, you'll notice the little check mark looking thing, which is the square root symbol. And then type in 3 and hit enter. And what should happen, you should get like 1.732050808. Now you might look at that end part and you might think, well, it's repeating there, 0808. It's actually not. And we could look, probably could look on the computer or something more accurate. This is, the calculator is rounding that last digit off. And so actually it's probably a 7 after that instead of an 8 actually. Anyway, always if it doesn't come out even, you got all this decimal stuff, it's actually just going to keep going, not repeat, which makes it irrational. So example 3, they want us to classify these numbers as rational or irrational, just like we did before. So that negative 81,572 is rational. Again, we could say we could write it as that over 1, or just it doesn't have any decimals, so obviously it's rational. Square root of 16 we talked about comes out even, that would be 4. So that you could put as 4 over 1 if you want. Square root of 11, a number times itself, both numbers have to be the same, that equals 11, doesn't work. 3 times 3 is 9, 4 times 4 is 16, so that would be irrational. Decimals keep going, don't repeat. And then that 5.636336333, that would probably have another 3 on it actually. That one would be irrational. Oh, I just looked at it wrong, sorry, they're okay. That's irrational because the decimals keep going and do not exactly repeat themselves. So if we look at the try it, they want us to classify these rational or irrational. This time they don't give us a table, so no cheating. We don't know how many there's going to be of each of these this time. So if we go through these, one example, the negative 0.75 repeating, 5 parts repeating always will be rational. 2/3 would be rational. That's actually just our definition of rational. We have a fraction with 2 integers. If you divided it out and got a decimal, that would actually be 0.6 repeating. It would be a repeating decimal, but we don't have to do that technically. That's right at our definition of rational. Square root of 25 is rational. Square root of 25, a number times itself, that equals 25. So, 5 squared, or 5 times 5 equals 25. So that would be rational. Square root of 2 would be irrational. We can't take a number times itself to equal 2, so that doesn't work. Again, you could do it on your calculator. It's going to be 1.4 or 1.4 or something. And our last one, 7,548,123 would be rational. No decimals or anything there. Put it over 1 if you like, it's rational. Key concept, just recapping things again, basically Venn diagram that we've already seen. Look at the do you know how number 4, and they're asking if that number is rational or irrational. This would be irrational because we have just what we talked about. We've got a non-terminating, non-repeating decimal. Keeps going and it doesn't repeat. If we go to number 6, again, they want us to classify the numbers rational or irrational. First number is a repeating decimal. Repeating is rational. Our second decimal is rational as well. The decimal ends or terminates. We could write it as 375 over 1,000 if we wanted to. Next one listed here, there is a pattern with it, but it's not the exact same numbers repeating themselves, so that's irrational. Square root of 62, a number times itself, that equals 62. Well, 8 times 8 is 64. Close, but we're not playing horseshoes, so that does not work. Irrational. And negative 13 over 1, that is exactly our definition of rational. We'll look at a couple problems here that are not in your books. So number 9 asks which of these numbers are rational. The first one, it has the 3 dots at the end, but notice that is repeating. They could have actually written that as 3.2 repeating. So that is rational. That's good. The second one, pattern, but it's not the same thing every time, so that is not going to work. And the last one, decimal ends, so that works as well. So that would be 1 and 3, which is choice D. And if we look at number 10, rational or irrational, 2/3 is rational. The decimal one, next decimals keep going. That's actually, I think that is pi there, just in decimal form. 0 is rational. Square root of 1 is rational. 7.4 repeating. Repeating is always rational. 15 is rational. Square root of 3 is irrational. So this gives you an idea of how to categorize with irrational and rational numbers.